In this section, we are going to look at other types of equations. So far in Chapter 1, we've solved the linear equations. In Section 1.2 and in Section 1.5, we solved quadratic equations. So now we're going to look at some different types. The first type we're going to look at is polynomial equations, and we're going to solve those by factoring, by grouping. The second type of equation we're going to look at are radical equations. Those are equations that contain radical symbols like square roots. The third type we're going to solve are equations that contain rational exponents. And the word rational again means fractions. So that's an equation that has an exponent that's a fraction. Then we're going to solve equations that are quadratic in form. They're not quadratic equations, but they fit the form of the general quadratic equation. Then we're going to solve equations that contain absolute values. Polynomial equations. What makes an equation a polynomial equation? Well, if we set two polynomials equal to each other, that's a polynomial equation. Now, what makes something a polynomial? What makes something a polynomial is that none of the exponents can be negative numbers or fractions. All the exponents must be whole numbers, 0, 1, 2, 3, 4, etc. If you put the polynomial equation in general form, that means you get all the algebraic expressions on one side and 0 on the other. Once we have it in general form, where we have 0 on one side of the equation, we can factor it, and we're going to factor it by grouping. The degree of a polynomial equation is the same as the highest degree of any one of its terms. What that means is it's the biggest exponent. So if the largest exponent in this polynomial equation is 3, it's a third degree polynomial equation. If the largest exponent's 4, for example, then it's a fourth degree polynomial equation. A polynomial equation of degree 1, the exponent on our x is 1, is linear. A polynomial equation of degree 2, the largest exponent on any one of our x's is the number 2, that's quadratic. Some polynomial equations of degree 3 or higher can be solved by moving all the terms to one side and getting 0 on the other, or getting it in general form. Once it's in general form, you can factor it and set each factor equal to 0 per the zero product principle. Zero product principle says that if you have factors and their product is equal to 0, one of the factors must be equal to 0. So these three equations at the bottom of this slide are all polynomial equations. The first equation is linear because the exponent on the x is the number 1. The second equation is quadratic because the largest exponent on any one of the x's is 2. The last equation is a third degree polynomial equation. The largest exponent on any one of my x's is the number 3. So that makes the degree of that equation 3. All right, let's solve one. We're going to solve 2x to the third plus 3x squared equals 8x plus 12. So the first thing we must do to solve this polynomial equation is to get it in general form. That means to get everything on one side and 0 on the other. So what we need to do is we need to move the 8x from the right-hand side to the left. And we do that by subtracting 8x from both sides. We're also going to move the plus 12 to the left-hand side. And we do that by subtracting 12 from both sides. A short way of saying this, shortcut way of saying, I'm going to move a positive 8x from the right-hand side to the left-hand side by making it negative. The reason it works that way is because I'm actually subtracting it from both sides. I'm going to move the plus 12 to the left-hand side by making it negative. Again, the reason it works that way is because I'm subtracting 12 from both sides of the equation. So what I'll get when I do that is 2x to the third plus 3x squared. I've moved the positive 8x to the left-hand side, so it becomes minus 8x. I move the positive 12 to the left-hand side, so it becomes minus 12. Right, so now I have this polynomial equation in general form. Now I need to factor it. The only method we have today at this moment to factor a third-degree polynomial equation with 4 terms is to factor it by grouping. So how do we factor by grouping? You group the first 2 terms in your polynomial together. So we're going to group the 2x to the third and the 3x squared. And we're going to factor from that the greatest common factor. So the only factor that 2x to the third and 3x squared have in common is x squared. So I'm going to factor that out. When I factor an x squared from a 2x to the third, what do I have left over? All I have left over is 2x. And I can check that to make sure it's correct by doing a quick distribute. Does x squared times 2x equal 2x to the third? Yes. All right, now I'm going to factor the x squared from the plus 3x squared. If I factor in x squared from plus 3x squared, what I have left is a plus 3. Again, I'm going to do a quick check. Does x squared times 3 equal 3x squared? Yes. Okay, now I'm going to group the second 2 terms together. The second 2 terms are negative 8x and negative 12. Since both of those terms are negative, I am going to factor a negative out. All right, now what is the greatest common factor between 8 and 12? The largest number that both 8 and 12 have as a factor is 4. So I am going to factor out a negative 4. When I factor a negative 4 from negative 8x, what am I going to have left? A 2x. Does that check? Is negative 4 times 2x negative 8x? Yes. Now I'm going to factor a negative 4 from a negative 12. When I factor a negative 4 from a negative 12, I have left a plus 3. And I do a quick check. Is negative 4 times plus 3 negative 12? And the answer is yes. So I have factored this correctly so far. Now, factoring by grouping, what has to happen next is the 2 factors that are inside parentheses have to be identical. If they are identical, I may factor out that binomial factor. So in the first term, I have a binomial factor of 2x plus 3. In the second term, I have a binomial factor of 2x plus 3. So I may factor out that binomial factor. So I'm going to factor a 2x plus 3. Now, what do I have left in that first term if I remove the 2x plus 3? What I have left is x squared. What happens if I remove the 2x plus 3 from the minus 4 times 2x plus 3? What I have left, if I get rid of that stuff inside parentheses, is a minus 4. Now, I may also factor the x squared minus 4. I may recognize that that is the difference of 2 squares, and I have a formula for that. The difference of 2 squares, this is a formula. A formula means I can use it for anything. Factors to the sum of the square roots times the difference of the square roots. So I should be able to factor x squared minus 4 to x plus 2 times x minus 2, which I can. Now I have this polynomial factored completely. There is no more factorization that I can do. And one thing I might note is each of the factors are now linear. That's kind of important. 2x plus 3 is a linear factor. It's linear because the exponent on the x is 1. X plus 2 is linear because the exponent on the x is 1. X minus 2 is linear because the exponent on the x minus 2 is 1. So I'm going to write this again down on my next slide. Now the zero product principle says that if I have a product and that product is equal to the number 0, then one of the factors must be 0. So to solve this, I set each of these linear factors equal to 0. So I set the 2x plus 3 equal to 0, the x plus 2 equal to 0, and the x minus 2 equal to 0. And then I solve the resulting 3 linear equations. Subtract 3 from both sides, divide by 2. So one solution is -3/2. Subtract 2 from both sides. So another solution is -2. Add 2 to both sides. And another solution is +2. So the solution set consists of the numbers -3/2, -2, and 2. Now I should check these 3 solutions to ensure that they are correct. And I can plug each one of those back into the original equation and check that my solutions are correct. The next type of equation that we're going to solve are radical equations, or equations that contain roots, like a square root or a cube root or any higher root, a fourth root, fifth root, etc. For example, the square root of square root of x equals 9, I will get it right. The square root of x equals 9 is a radical equation because on the left-hand side of this equation, we have the variable that we're solving for underneath a square root symbol. So how do I get that variable that's underneath that square root symbol out of the square root symbol? And the simplest way to do this is to square both sides, because you know that if you square the square root, then you get the value underneath the square root. So the square root of x squared is just x. Now the problem with this method is that you can introduce extraneous solutions when you square both sides of an equation. For example, would you agree that -2 does not equal 2? Would you agree with that? But what happens if I square both sides? Well, that is true. So the problem with this is that when you square both sides, you may be potentially squaring a number that's negative, and you don't know that because it's in the form of an x. So what's the point of this? The point of this is if you're solving a radical equation where you square both sides of the equation, you have to check your solutions. And I don't mean you can check them to make sure you're right. I mean you have to check them, because if you introduce extraneous solutions that are not solutions and you type that into MyMathLab, you get it wrong. So you must check your solutions every time you solve a radical equation by raising both sides of the equation to an even power. So if you square both sides, raise both sides to the 4th power, etc. All right, let's look at a couple of examples. To solve a radical equation, if necessary, you need to rearrange things so that you get the radical isolated on one side of the equation. You want the radical isolated because you want to be able to square both sides or cube both sides if it's a cube root. Okay? Then you're going to raise both sides to that root. If it's a square root, you're going to square both sides. A cube root, you're going to cube both sides. Fourth root, you're going to raise both sides to the 4th power, etc. You're going to solve the resulting equation. If you still have a radical, you repeat the step. And we're going to do that in the second example we're going to do. And then when you're done, you need to check all your proposed solutions. You have to check your solutions. I'm not kidding. You have to check them, because when you raise both sides of an equation to an even power, you can introduce error. So you have to check your solutions. All right, so this is what we're going to solve. The square root of x plus 3 is equal to x. So the first thing we need to do is we need to isolate the radical. And we need to isolate it so that we can square both sides and get rid of it. So what I want to do is I want to move that plus 3 from the left-hand side to the right-hand side of the equation. And I do that by subtracting it from both sides. So I'm going to move the plus 3 from the left side to the right side by making it negative. All right, so next I raise both sides of my equation to whatever power my root is. Since I'm taking the square root, I'm going to raise both sides of my equation to the second power. And as soon as I do this, I introduce a possible error. All right, now when I square a square root, I'm going to get the radicand. So the stuff underneath the square root. So the square root of x plus 3 squared is just x plus 3. This is the reason you do this. You do this to get rid of the square root. If I square a square root, I eliminate the square root. So on the left-hand side, I have x plus 3. On the right-hand side, I'm going to square that binomial. I am going to use my formula. I am not going to square a binomial by foiling it. It's too much work. So what's my formula? I have 2 of them. Let me write it down correctly, though. Why we have erasers. Okay. A plus b squared is a squared plus 2ab plus b squared. So I square the first term. I multiply the 2 terms together and then multiply that by 2, and then I square the last term. If the middle is a minus b, then the middle term on the trinomial I get when I'm done is negative. So a minus b squared would be a squared minus 2ab plus b squared. So I'm going to use that formula to square. And I'm going to erase it to make myself a little bit more room. Okay, so I square the x. I multiply the x and the minus 3x. I double that. Then I square the 3. So now I've squared both sides of this equation. I have x plus 3 equals x squared minus 6x plus 9. I'm going to solve that now. All right, this is quadratic, and it's quadratic because the largest exponent on any one of my x's is a 2. So to solve a quadratic equation, I have 3 methods. I can solve it by factoring it. I can solve it by using the square root property. I can solve it using the quadratic equation. I'm going to see if I can factor it. So I'm going to move the positive x from the left-hand side of the equation to the right-hand side of the equation by subtracting it for both sides. All right, now I'm going to move the 3 to the right-hand side by subtracting it from both sides. Now I'm going to factor this. Now, I always factor by trial and error. I reverse FOIL it. So I need 2 factors of 6 that will add to 7. Now, you'll notice the middle term in this trinomial is negative. The last term in this trinomial is positive. So in my 2 binomials, I must have x minus, And the reason I have to have that is because when I have outside and inside and I add those together, if I add two negatives, it's going to be negative. But when I multiply last by last, negative times negative will give me positive. So I have to have x minus for this to work. Two factors of 6 that add to 7, well, that would be what, 6 and 1? All right, so now how do we solve this? To solve this, we set each factor equal to 0. So I set the x minus 1 equal to 0. I set the x minus 6 equal to 0. And I get x is 1 or x is 6. I'm going to write that up here. X equals 1 or x equals 6. All right. I can't just type those into MyMathLab and hit the submit button and go along my merry way. I must check those two solutions to see if I've introduced any kind of error. Is one of those solutions extraneous? All right, so I'm going to write down my original equation. There's my original equation. And the two solutions I got were 1 and 6. And I'm going to check both of those by plugging it back in. So I'm first going to check the 1. So I have the square root of 1 plus 3 equals 1. Well, I don't think that works. Do you think that works? Okay, what's the square root of 1 plus 3? Is that the square root of 4? Is that 2? That doesn't work. So 1 is not a solution. Let's check 6. Put the 6 back in for x. Square root of 6 plus 3 is the square root of 9. Square root of 9 is 3. So the solution set to this equation is the number 6. 1 is not a solution. 1 is not a solution. So the only solution is the number 6. Okay, this is the hardest problem you're going to do all semester, I promise. What if you have two radicals in your equation? Now, this takes quite a bit of paper to do this, but I just want to remind you that you need to follow all the rules that you have for algebra. To solve this equation, you're going to isolate one of the radicals. You're going to square both sides. You're going to square whatever binomial you have on the whatever side. You're going to square it using your formula. You're going to end up with a radical. If you have two radicals and you square both sides, you're still going to have a radical when you're done. You're going to do the same thing. You're going to isolate the radical and you're going to square both sides. So what I'm going to do is I'm going to move this radical, the minus square root of x plus 4, to the right-hand side of this equation by making it positive. So I'm going to add the square root of x plus 4 to both sides. And so what I end up with is this. All right, so now I'm going to square both sides. On the left-hand side, when I square a square root, I just end up with the radicand. But on the right-hand side, I am going to use my squaring of a binomial formula. A plus b quantity squared is a squared plus 2ab plus b squared. So to do that, I am going to square the first term. I'm going to square that. But when I square the square root of x plus 4, I just get x plus 4. Now I'm going to multiply the two terms together, and I'm going to double that. So I have the square root of x plus 4 times 1. Now I'm going to multiply that by 2. So what I get when I multiply those two terms together and then double it is 2 times the square root of x plus 4. Now I'm going to square the 1. Now I'm going to combine like terms and isolate the radical again. So what do I have? Over on the right-hand side, I have a 4 and a 1. So I'm going to write x plus 5 plus 2 times the square root of x plus 4. Now I need to isolate that radical, that square root of x plus 4. So I'm going to move the x from the right-hand side to the left by subtracting it from both sides. I am going to move the 5 from the right-hand side to the left by subtracting it from both sides. Now, this problem is nice because I actually have a 2 that I can divide out on both sides. So if I divide the left-hand side by 2 and I divide the right-hand side by 2, that may make the squaring of this a little bit easier. And I can divide 2x minus 4 by 2 because the 2x and the 4 both contain the factor of 2. So I can actually factor that out and cancel it. And the 2's cancel on the right-hand side. So I end up with x minus 2 equals the square root of x plus 4. And I repeat the process. I now square both sides of the equation, and then I'm going to solve the resulting quadratic equation. So I'm going to square both sides. On the left-hand side, I'm going to square that binomial. So I get x squared minus 4x plus 4. That's going to be equal to x plus 4. And I'm going to solve that equation. So I'm going to go into the new slide. I'm going to go ahead and go over there. So I have, what do I have? X squared minus 4x plus 4. Equals x plus 4. There we go. Now I'm going to solve this. I'm going to subtract x from both sides. I'm going to subtract 4 from both sides. And I end up with x squared minus 5x equals 0. And that doesn't bother me. Sometimes we get tense when the constant term goes away, but to factor a binomial that doesn't have a constant, just factor out the greatest common factor, which would be x. Set each factor equal to 0 and solve the resulting linear equations. So the two solutions I get are 0 and 5. So I need to check both of those and see if they work, because one of them may be extraneous. So let's first check the 0. And I went ahead and put the equation on this slide so that we could see it. So we have the square root of 3 times 0 plus 1 minus the square root of 0 plus 4. Is that equal to 1? Well, what do I have? The square root of 1 minus the square root of 4 equals 1. Well, no, it doesn't. So that's 1 minus 2. That does not equal 1. So 0 is not a solution. So that is a solution we introduce by squaring both sides. So let's check 5. 3 times 5 plus 1 minus the square root of 5 plus 4. Does that equal 1? So we have the square root of 16 minus the square root of 9. Is that equal to 1? Yes, 4 minus 3 equals 1. So 5 is a solution to this quadratic equation. So our solution set is the set that contains the number 5. All right. The next type of equation we're going to solve are equations that contain rational exponents. So by definition, if you have something raised to an exponent that's rational, it's a fraction, you can evaluate that exponent one of two ways. So if I have a to the m over n, I can evaluate that by taking the nth root of a and then raising that value to the power m, or I can take the nth root of a raised to the m power. To solve a radical equation with rational exponents, what we're going to do is we're going to isolate the expression that contains the rational exponent. So we're going to have the x to that power all by itself. Then we're going to raise both sides of the equation by the reciprocal of that rational exponent. Because what we know, let's say we have a squared, and we raise that to the 1/2 power. By the laws of exponents, when we raise a power to a power, we do that by multiplying the two exponents together. So this is a to the 2 times 1/2, which is a to the first power, or a. So when we multiply power by the reciprocal of that power, when we multiply the exponents, we get 1. All right, now here is the only stipulation to this, and this is in the notes sheet that you have available for Chapter 1. If you don't know where the note sheets are, if you're in Blackboard and you click on Course Content and you click on the Chapter 1 folder, the notes for Chapter 1 should be third down from the list in that list of things that you can click on. You can also get to the notes by clicking on any one of the Chapter 1 sections. All right. So if we raise both sides of an equation to the reciprocal of the power, and the numerator of the original exponent is even, then when we solve this, we have to put a plus or minus in front of that. So if we're solving the equation x equals, let me say this here, x to the m over n equals some number k. When we raise both sides of that to the n over m, and m is even, you have to put a plus or minus in front of your solution, because both the positive and the negative will actually work in the original equation. If m is odd, you don't have to do that. So for example, if we're solving x equals 2 over 3 equals, I don't know, 5, we'll just make something up. If I raise, since m is even, it's an even number, if I raise both sides of this to the 3/2 power, over here on the right, I have to put a plus or minus in front of it. Okay, so if I raise both sides of an equation to a power and the original exponent, its numerator is an even number, then I have to put a plus or minus in front of my solution. Okay, so let's solve this equation that contains a rational exponent. Now I don't have to put the plus or minus here. And the reason I don't have to put the plus or minus is because the exponent is 3/2. The numerator is an odd number, so I don't need to worry about the plus or minus. So to solve this type of equation, I need to isolate the x to the 3/2 all by itself. I have to get the expression with the rational exponent all by itself. So I'm going to move the minus 25 to the right-hand side of this equation by adding it to both sides. Okay, again, I need to have the x to the 3/2 all by itself. So I'm going to get rid of the 5. So since I'm multiplying, I'm going to divide. All right, next, I'm going to raise both sides of this equation to the reciprocal of my rational exponent. Since my exponent is 3/2, I'm going to raise both sides to the 2/3 power. I do not have to put a plus or minus in front of the 5 to the 2/3 because my original rational exponent, the numerator, was odd. If the numerator is even on the original rational exponent, I must put a plus or minus in front of my answer. Okay, so x, when I raise x to the 3/2 power to the 2/3 power, raising a power to a power, I multiply the exponents. When I multiply a number times its reciprocal, I get 1. So I get x equals 5 to the 2/3, which is a perfectly acceptable way to write this. You could also write this in terms of a radical. The denominator of a rational exponent is the root that I'm taking. So I could write this as the cube root of 5 squared, which is the cube root of 25. Okay. Equations that are quadratic in form. So what makes an equation quadratic in form? If you remember, your quadratic equation, when it's in general form, looks like this. And if you look at the first two terms in a quadratic equation and then look at the x's, what's the relationship between the x in the first term and the x in the second term? Not only that, but what's the relationship of the exponents? So the first term contains an x squared. The second term contains just an x. X is actually x to the first power. So if the exponent in the first term is 2 times the exponent in the second term, that equation is quadratic in form. Repeat. If the exponent in the first term is 2 times the exponent in the second term, that equation is quadratic in form. And we're going to use a substitution to solve it. Okay, let's look at these two examples. The first example says x to the 4th minus 10x squared plus 9 equals 0. That equation is quadratic in form. It's quadratic in form because the exponent 4 is 2 times the exponent 2. 4 is 2 times 2. So that equation is quadratic in form. And we can solve it by making a substitution. The substitution we make is we let u, every time you see a u in algebra, it represents an algebraic expression. So we're going to let u equal x squared. So that x to the 4th minus 10x squared plus 9 equals 0 can be converted to the quadratic equation u squared minus 10u plus 9 equals 0. You can solve that by factoring. And once you have it solved by factoring and you know what u equals, you can back substitute to find x. Look at the second equation. I have 5x to the 2/3 plus 11x to the 1/3 plus 2 equals 0. Is 2/3 2 times 1/3? Yes. 2/3 is equal to 2 times 1/3. So that is an equation that's quadratic in form. So I can solve it by making a substitution. I let u equal the second variable. Every time I do this and I make this substitution, I let u equal the second variable. So in the first example, the second variable was x squared. I let u equal that. In the second example, the second variable is x to the 1/3. So I let u equal x to the 1/3. So the equation gets converted to a quadratic equation, 5u squared plus 11u plus 2 equals 0. And I can solve that by factoring it. So I'm going to take the equation that's quadratic in form and convert it to a quadratic equation by substituting u. What does u mean? U means some algebraic expression. Let u equal the second variable. All right, let's look at an example. This is an equation that's quadratic in form because the first variable, its exponent, is 4. The second variable, the second term, the x squared, its exponent's 2. 4 is 2 times 2. So this is quadratic in form. If the exponent in the first term is twice the exponent in the second term, it is quadratic in form. So what we do is we make the substitution. We let u equal our second variable, our x squared. So then we can convert this equation to one that's quadratic in form. If u equals x squared, then u squared is equal to x to the 4th. And how do I get that? I square both sides. So now I can make the substitution. X to the 4th is u squared minus 5u plus 6 equals 0. And then now I solve this by factoring it. We have u. They're both going to be minus because the middle term is negative and the last term is positive. I need 2 factors of 6 that add to 5. That would be what, 3 and 2? Now I'm going to solve the resulting equations. Add 3 to both sides, and I get u is 3. Add 2 to both sides, and I get u is 2. Okay, I'm not done at this point because I know what u is, but I don't know what x is. But I do know right here that x squared is equal to u. So I have x squared is equal to 3. I have x squared is equal to 2. So now I can solve those 2 equations. And I'm going to solve them using the square root property. Square root property says that if I have x squared equal to 3, then x is plus or minus the square root of 3. If I have x squared is equal to 2, then x would be plus or minus the square root of 2. And I do have to have that plus or minus. The square root property says that if I take the square root of both sides, I have to put the plus or minus on the right-hand side of the equation. All right, so now I have 4 solutions. 3, square root of 3, negative square root of 3, square root of 2, and negative square root of 2. And I'm just going to write this using the plus or minus just to save a little bit of work. Now, does it surprise you that you solved a 4th degree polynomial equation and you got 4 solutions? Talk about that more in chapter 3. Okay, now let's solve this equation that's quadratic in form. It's quadratic in form because the first exponent, 2/3, is 2 times the second exponent, 1/3. 2/3 is 2 times 1/3. Okay, so we're going to make a substitution. We're going to let u equal the second variable. So now if I square both sides, u squared is x to the 1/3 squared. We multiply exponents when we raise a power to a power. We get x to the 2/3. So now we can convert this equation to an equation that's quadratic. So it's going to be 5u squared plus 11u plus 2. And I hope you can just recognize how to write that equation as a quadratic. All right, now we're going to factor this. They're all going to be plus because everything's positive. I have a 5u squared in that first term. So the only 2 things that are going to multiply to 5u squared is 5u and u. And then I need factors of 2. I need to place those in those last positions. so that when I add outside and inside, I get 11. So I think I'm going to put a 2 there and a 1 there. And I'm going to do a quick FOIL in my head to verify that that is correct. So now I'm going to set each factor equal to 0. Solve the resulting linear equations. All right, so I get that u is either -1/5 or u is -2. And it doesn't tell me what x is. It tells me what u is. So I have to back substitute again into this equation to solve for x. So x to the 1/3 is equal to u. So x to the 1/3 is either equal to -1/5 or x to the 1/3 is equal to -2. Now, this is a rational equation like we just solved a few slides back. So to solve this type of equation, we raise both sides to the reciprocal of our rational exponent. So our rational exponent is 1/3. The reciprocal of 1/3 is 3. So I'm going to raise both sides of the equation to the 3rd power. All right, when I raise a fraction to an exponent, I raise, that should be a 3 right there. I raise both the numerator to that power and the denominator. A negative raised to the 3rd power is going to be negative. Negative times negative times negative is negative. Raise 1 to the 3rd power, I get 1. Raise 5 to the 3rd power, I get 125. So there's one solution. Do the same thing over here. Raise each side to the 3rd power. -2 to the 3rd power, -2 times -2 times -2 is -8. So our two solutions to this equation that's quadratic in form are -1 over 125 and -8. All right, absolute value. I see a lot of ways that people solve absolute value equations. Do it the way I tell you to do it. The absolute value of x describes the distance x is from 0 on the number line. That is what absolute value is defined to be. To solve an equation that contains an absolute value, first of all, we're going to rewrite that equation by removing the absolute value bars. All right, let's talk about this a minute. If c is a positive real number and u, again, here comes the u again, u is an algebraic expression. Whenever you see the variable u used in algebra, it's usually going to be used to represent some algebraic expression. What's an algebraic expression again? An algebraic expression is a combination of variables and numbers using addition, subtraction, multiplication, and division. All right, so we have the absolute value of u is equal to c. The stuff inside the absolute value bars could be c. The absolute value of c is equal to c. However, the stuff inside the absolute value bars could also be equal to -c, because the absolute value of -c is positive c. So for example, what value can I put inside the absolute value bars and get the number 5? Well, I can take the absolute value of 5 and get 5, but I can also take the absolute value of -5 and get 5. So the stuff inside the absolute value bars could be +5. It could also be -5. So to solve an absolute value equation, you take the algebraic expression that's inside the absolute value bars. the algebraic expression inside the absolute value bars. You set it equal to the positive constant, you set it equal to the negative constant, and then you solve it. So you take the 2x plus 7, you set it equal to 5, you take the 2x plus 7, and you set it equal to negative 5. Any other way you try to solve this is incorrect. You take the expression inside the absolute value bars, set it equal to the positive constant, take the stuff that's inside the absolute value bars, the algebraic expression, set it equal to the negative constant, solve. Does it surprise you that there are two numbers that will satisfy this? It should not. You can stick, for example, -1 in there. -1 will work. Because when I put -1 in for x, -2 plus 7 is 5. The absolute value of 5 is 5. Could I also put in, what's the other answer going to be? -6. If I stick x equals -6 in there, 2 times -6 is -12. -12 plus 7 is -5. What's the absolute value of -5? 5. So if you solve an absolute value equation, how many answers are you going to get? 2. Are you going to get 1? Are you going to get 2? Yes. You're going to get 2 answers. All right. So let's solve an absolute value equation. To solve an absolute value equation, you take the algebraic expression that's inside the absolute value bars, you set it equal to the positive constant, you set it equal to the negative constant. Solve the two equations. Now, I should take a step back real quick. If the absolute value is not isolated all by itself on one side of the equation, you need to do that. You have to have the absolute value all by itself on either the left-hand side or the right-hand side. Right? Let me finish this. So x equals 3 is one possible solution. -5 plus 1 is -4. Divide both sides by 2. And I get x is -2. So I can have two solutions, 3 and -2. And will they both work? Yep. So let's go up here and let's look at what happens when I put those two numbers in my original absolute value equation. If I put 3 in there, 2 times 3 is 6. 6 minus 1 is 5. The absolute value of 5 is 5. If I put -2 in there, 2 times -2 is -4. -4 minus 1 is -5. What's the absolute value of -5? 5. So if you solve an absolute value equation, how many answers are you going to get? I'm going to say it again, 2. You're going to get 2 because there are two numbers that you can plug into those absolute value bars and get +5. You can plug in 5, you can plug in -5. And we're going to skip that. That's a radical equation. You can look at that. And that is the end of section 1.6.